Okay. So let us start on continue with this section on bilging. We have already done some problems relating to bilging. So there is in this section there is one more problem. Okay. Now let us look at this problem. A box vessel of length 140 meter with breadth 20 meters, depth 14 meters is floating at a draft of 5.8 meters. You are given the kg as 8 meters. It is a midship compartment of length 24 meter, breadth 7 meter, has a watertight flat at a height 6 meter above the keel. Find the bilged draft and the GM in the intact and bilged condition. Okay, I will explain what this problem is. So, just like the previous, you have a box shaped vessel. Okay. So, there is a box shaped vessel and you are told that there is a compartment in the middle, this much. So, there is a compartment in the middle and let us call this the water line. So, there is a what they mean by a flat is that there is some kind of ceiling, okay, above the, it is like this. So, this compartment as such is covered here at some height. So, what this problem is trying to state is that usually we see that when a ship is bilged, it gets bilged completely, means this whole region gets bilged, whatever means up to the draft. If let us say that the draft increases to this, in this case, let us say that this is a final draft, you know that up to this in all our problems the we know that the compartment gets bilged up to this point, that is how we have done. In this problem the difference is that they have put a flat here, means there is some kind of a ceiling here such that when this is bilged, water cannot, it is a watertight flat, that means water cannot go above this. So, even though the draft is up to this much, in the compartment water will be only in this region, I mean if this region, water will be only up to this, and this region will be just like the other ship which is not at all bilged. That is the difference in this problem, just a slight twist. The difference will come in trying to calculate things like I and the height up to which it is bilged, things like that. That is only difference. So, there are two possibilities, as you can see. In the first case, the draft here is here, means it is below the flat. In that case, the problem becomes just like what we have done so far, means the problems where you had some compartment bilged and that whole compartment's buoyancy is lost, that volume is lost. So, that is the so it becomes exactly like that. But the second part of the problem, second possibility in this problem is when your draft is above the flat, this one, that becomes slightly different, because bilging then occurs only up to some point in between and some point in that compartment is still remaining. Therefore, it becomes slightly difficult to calculate the volume, I, etc. So, that is the only thing in this problem. So, let us check that. First of all, to solve this we use the formula. This formula we have done, if you remember, LBD initial gives you the total intact volume before, total intact volume means before bilging, okay, and so this gives you the distance dB, gives you the formula which states that well, I have said this in many ways. I have told that the easiest way to think of it is the final volume, the final weight of the ship after the water has gone in is equal to the weight initial plus the weight of water. That is the easiest way to look at this formula. So, that I have already described. So, in the book it states as, you will see that it is the same thing. It says that intact volume before bilging is equal to the intact volume after bilging. You just see that it is the same thing. Then therefore, in this case LBDI let us assume that LBDI becomes, we have to find the length. Let us look at the problem. Okay, length is 140. So, 140 into breadth is 20 into initial draft is given to be 5.8. Okay. So, this is your this is your initial volume before bilging, intact volume. Then the volume after bilging becomes LBDB minus LBDB, which is equal to LBDB is 140 into 20 into dB, which you do not know, minus LB. L is the so what is subtracted is the volume of the compartment that is bilged. So, you need to know the length of the compartment that is bilged, the breadth of the compartment that is bilged, and the height to which it is bilged. Now, this is the difference in this problem. Like usually this is the formula LB minus LB in capital L B dB minus small l B dB is the formula generally. Why? Because when it is bilged, usually in this problem, when it is bilged, the height up to which it is bilged, means the height up to which the water enters the compartment is equal to the height of the water line. Up to the water line, we assume that the water enters. I mean, it is normal, that is the way in which we have done, but in this problem there is a slight difference. Water cannot enter up to the water line, because at some point in between there is a watertight flat. They have said flat means just a ceiling such that water cannot go above that. So, when whatever happens, water enters only up to that point. So, the height up to which the water enters, or the height the volume, to get the volume of water, it is L, length of the ship of that compartment, B, breadth up to which the compartment is filled up, into the height up to which the water can fill up, which is actually the height of the flat. Okay. It does not dip up to the total height of the water line, because height of the water line comes up to this in this problem. Initially it is at 5.8, then when it sinks it goes above 6, this is said to be 6, the height of the flat is said to be 6, okay, 6 meters. At 6 meters there is a watertight flat, therefore, this is not dB in this problem, that is the only difference, it becomes some h, which is the height of the flat. Okay. So, this is the height up to which the water can flood the compartment. So, this will be, therefore, it will become 140 into 20 into dB minus small l is the length of the 24 into 7 into 6. Here L is the length of the compartment which is flooded, 24 is the length of the compartment that is flooded, 7 is the breadth of the compartment that is flooded, and 6 is the height of the flat, that is the height up to which the the compartment can get flooded, that is the height up to which it can get flooded, the height of the flat. So, this is equal to the initial volume. That formula, please, as I told you, it is very important.
But here we are assuming that water is going above that flat.
Yes.
But it may not.
No, you are assuming, but that is just intuitive. See, initial draft is 5.8 meters, the height of the flat is 6 meters. Now, when water enters, we are, I think it is reasonable to start with the assumption that it will go above 6. If you do not assume, you will see that your answer will come above 6, therefore, your answer is wrong. Therefore, but you can easily see 5.8 to 6 meters, you will definitely go above that. Okay. So, that is why we have directly assumed that it does definitely go above that, otherwise yes, you are right. Then, but I think you might end up getting dB as negative or something in that. You just do, you will have to do that and see, when you, if you assume that it is below, you might get dB negative, which means that it has actually gone above the flat, that it will not match, you will not be able to solve it. So, this minus this becomes equal to the initial volume, which is 140 into 20 into 5.8. Okay. So, when you do this, you will get dB as equal to 6.16 meter. So, this much the height of the water line has gone above the height of the flat. Therefore, that is the slight catch in this problem. So, you see that this is the height up to which the ship sinks, dB is the final draft, the bilged draft it is called. Now, the other thing to need another thing you are going to calculate is to you are asked to find the GM. Yes, you are asked to find the bilged draft and you are asked to find the GM. Therefore, in this to find GM you need to find kg and km. Now, km, remember this is a box shaped vessel, we are talking about intact condition first. It will be very straightforward formula. You have the box shaped vessel, you have the km given by this formula, you do this, you will get it to be. So, this becomes the km of the vessel. Then kg is given in the problem itself, kg is given to be 8 meters. Therefore, gm of the vessel in the intact condition is km in the intact condition minus kg in the intact condition. Kg does not change, in this case it becomes 0.647. So, this is your GM in the intact condition. Then km you need to find the km in the bilged condition. Okay. Now, we can use the formula GM is equal to Km, this is in the bilged condition, Kb plus Bm minus Kg. Note that we are doing everything using buoyancy. So, Kg does not change, Kg is still 8 meters. So, this we know. So, you need to find Bm and you need to find the Kb. Okay. Now, Bm can be found as I by del. Note that in this case LB, the water line, the water plane, rather the water plane area does not include a, it is like this, it is just like in an ordinary ship, means it does not have a lost volume or anything. Therefore, it is just the ordinary ship, it is so it becomes L B cubed by 12 divided by del will be L B d I. Okay. This, because it is a method of lost buoyancy, the volume is the same as before. So, this is Bm, this you can directly calculate, very straightforward. So, this will give you your Bm. Now, the next thing to calculate is your Kb, that is a slight problem in this. Kb is the, you know that it is the centroid of the volume. Okay. Now, what are we doing? We are using the method of lost buoyancy, which is saying that it is the method of lost volume. So, some volume is lost from the ship and therefore, so you know the initial volume, you know you have to find, you know its Kb, you know the lost volume, that is, I will tell you what it is. We know the lost volume, that is how much the volume of the ship is lost because of water has entered, or that is the volume of water entered, rather it is the volume of water entered, and you need to find its Kb, and using a resultant of these two you can find the net Kb like this. That is, the first one is to find the you have to find the volume of the ship, okay, therefore, volume Kb and moment, if you write like this, L into B into dB. So, it will be 1, what is L? L is 140 into 20 into dB. We have calculated dB 6.16. So, this gives you the initial volume of the ship, or that is, the ship is like this now. This is the water line and this is the compartment and this is the flat. Okay. Therefore, this much volume is lost from the ship. Now, what we are doing right now is, I mean the easiest way to do is, you find the Kb of this. How do you find the Kb of this?
Since it is box shape
it is a box shape vessel. So, you know the kb, you need to find dB. dB is given as 6.16. So, its kb is 3.08. Okay. So, this it's a sorry, it's not a ship as such, it's a box shape vessel in this case. So, it's like this, it's not a ship. So, it's okay. So, in this case you know it's a box shape vessel. So, you know its kb, you know this kb, then therefore, you just multiply these two, you will find the moment. Then you have this volume is the volume of water entered, it is equal to the volume lost from the ship. So, this which is L into B into H, remember H is the height of the flat. So, that you do, and the best way is to put it as negative, because this volume is lost from the ship. So, this becomes negative in this case, whatever it becomes, and the height of the flat, this height we have just seen, it's 6 meters. So, its kb is 3 meters. Then you find its moment and you do sigma moment, means this one, this is sigma moment, this is sigma volume. So, sigma moment divided by sigma volume will give you the total net moment, I mean this will give you the net kb. This is the total kb of the box shape vessel after the water has entered in up to the flat. Okay. So, once you have that, you get the kb, then so you know kb, I have already told you how to get gm, no bm and kg is already given. Therefore, gm of the vessel finally in the bilged condition becomes kb plus bm minus kg. So, this is the final kb, this kb, bm, kg. Okay. See, the thing is, you cannot, we had a formula km minus kg equal to gm. You have a problem calculating the km for such a bilged condition, because this is not an ordinary kind of ship. First of all, it's not an ordinary box shape vessel, that is what I mean. It's a box shape vessel in which you have lost some volume, and it's not even lost up to the water line. So, it's not that direct formula of km is equal to d by 2 plus b square by 12 d cannot be used here. That is why we had to find it. This formula always holds good, that is gm is equal to kb plus bm minus kg. It is true always. So, whatever be the shape of the vessel or whatever be the condition, you can always use this formula gm equal to this. Now, and note that in all your, as far as this course is concerned, you are always going to do problems wise, though I mean theory wise you need to know the method of added weight as well, in which that we have done. And so, you need to know the method of added weight as well, but as far as problems are concerned, when you are doing the problems, you do it using only the method of lost buoyancy. That is what I have done. All the problems I have done so far is using the method of lost buoyancy. So, the things that you need to remember again, I am stressing, one is that volume which is filled with water is lost from the ship. So, that volume is not a part of the ship anymore. So, as a result of which, as a result of losing that volume, the net kb of the vessel will change. Okay. The kb, because the volume is lost from the ship, will change, but kg does not change, means whatever is there in the ship, the part of the ship as which is there is still there. Weight we are not changing as far as the method of lost buoyancy is concerned, the weight is not at all changed. Therefore, the total weight remains the same, that is delta remains the same, the total weight of the ship, kg also does not change. So, this because otherwise it is very difficult, you will not be able to do these problems, because you will be searching for kg I and kg B, means you are gone, you will not be able to solve it. So, do one thing, some simple things I will tell you. So, kg in the intact condition or kg in the initial condition is equal to the kg in the bilged condition is equal to some fixed kg, which is the fixed kg of the vessel. Okay. So, this do not get confused at all, never change the kg, do not search for kg, it will always be given in the problem also, kg will be given. Then this, then km, no kb will change, kb initially and I think all your problems will be box shape vessel only, because Kb for other vessels becomes a little more complicated. So, Kb initial you will have something Kb, it won't be equal to your Kb in the bilged condition, because some volume is lost, directly it assumes that Kb is changed, because if volume Kb is the centroid of the volume. So, if Kb is if volume is lost, Kb is lost. So, Kb is decreased or it is changed. So, Kbi is not equal to Kbb. This you have to find the Kb. The best way, if you want to find the volume, always use this way, that is Kb is always equal to a sigma moment of volume divided by sigma volume. So, if you have some volume, you take the intact ship, this sigma moment of volume for the, so sigma moment for the intact ship minus sigma moment for the lost or the added the lost volume divided by sigma volume. This will give you the Kb for the bilged condition. This will give you Kb for the bilged condition, which is your distance from the distance of the center of buoyancy from the keel. That will give you Kb, and that will be different in your bilged and in your intact condition, because volumes are different, underwater volumes are different. So, Kb will be different. Then your Bms also will be different, because the position of B is changing. So, Bm will also change. Only thing that won't change is your G, position of your center of gravity does not change. So, but Bm changes, because the because B changes. So, Bm you will have to calculate it as I by del. Okay. So, this will change. So, this you have to calculate. Then I guess these are the things you need to remember in the doing these problems. So, okay. So, this problem is okay. Then okay. Okay. Now, I already defined for you something known as permeability. I said that it is the amount, it is the volume of the compartment that can be flooded with water divided by, as you can see there, it is a volume of compartment that can be, it is not, it is like that is a volume of compartment that can be occupied by water divided by the total volume of the compartment. Now, note that it will be like, it is because of this. First of all, there will be volume of the compartment given by LBD, means length, breadth and draft or depth, whatever is that size of the compartment. So, if we are talking about one compartment now, so there is a volume first of all given by length into breadth into the size, length, the height of the compartment, that is one volume. Then there will be different kinds of solid stuff in it, means like anything, okay, whatever you have solid other than, such that the total volume decreases from your LB into D to something else, decreased to a smaller value, because for instance some very big, some shape something is there. So, these kind of different kinds of things will reduce the volume further. From LBD it will decrease, LB into height of the compartment, it will decrease to something else. And then again further, if there is cargo in the compartment, if you put cargo in the compartment, the total amount of volume that can be filled with water decreases further. Okay. Now, what we really call as permeability here is, first in the numerator you have the volume that can be filled with water, means cargo is there, and then what is the volume that can be filled with water. The denominator is without the cargo, it still is not equal to LB into height. Okay. There still might be very solid constructions which will reduce it from LB into height, but it is the volume without with cargo divided by the volume without cargo. So, that roughly gives you the permeability, and the usually you will see that the permeability is around 95%, okay, 0.95 rough value of permeability. So, this is what you define as permeability, is equal to about 0.95 roughly for ships, this is the value. And now, permeability can be defined as, to do it mathematically, it is usually expressed in percentage. So, it becomes 95 percentage. So, 100 into now this is how it is. This SF is what is known as a stowage factor. That is what we call as SF, the stowage factor. The meaning of stowage factor is this: it is the volume which it is the total volume with these things, okay, different constructions in the room. Means you have a room, let us suppose there is a small very thick pillar here, that will reduce the volume in fact. So, that much pillar's volume is lost. So, that is one construction possible, something else here like that, okay, different columns here, different things will reduce the volume. So, that volume is roughly what you call as stowage factor. It is the amount of cargo really that you can put, okay. Then 1 by rho. So, this is SF, this represents the volume of the compartment, and minus 1 by rho, rho is the density of the cargo that is put, and therefore, 1 by rho is like a specific, means you assume that 1 ton of cargo is taken, okay. The whole, that is how stowage factor is also defined. So, if you have 1 ton of cargo, the volume, now you always express rho in terms of meter cube per ton, okay. In hydrostatics at least, not meter cube per kilogram, you write it as meter cube per ton. So, whatever is the density of cargo, and if you assume 1 ton, that will give you the volume, means this is 1 ton, you will obviously get 1 by rho to be the volume. No, rho is in tons per meter cube, sorry, I made a mistake, not in meter cube per ton, I made, sorry. Rho is always given in tons per meter cube instead of kilogram per meter cube, and therefore, if you 1 by rho, as you can see, will give you in meter cube per ton, and if you take 1 ton of cargo, this obviously gives you the total volume occupied by that, and stowage factor is also given in terms of meter cube per ton, okay, and therefore, the whole thing is defined in terms of per ton. So, you can assume, so this is a meter cube minus meter cube divided by meter cube, okay, that gives you the permeability, the total volume that can be occupied by water. That is roughly the meaning of permeability, how much volume can be occupied by water, okay. This is written as mu, that is the permeability, okay. Then okay, this is permeability, SF minus 1 by rho by SF. Then there is this problem, it says that now there is a box vessel of length 100 meters, 1 minute, sorry, okay, there is a box vessel of length 100 meters, breadth 9 meters, depth 6 meters, floating at a draft of 5 meters. Now, a full breadth midship compartment of length 20 meters contains cargo at a stowage factor of 1.2 meter cube per ton. It has a density of 2 tons per meter cube, and you are asked to find the bilged draft, okay. This is the problem. Now, first of all, in this problem you can directly find the permeability. So, permeability is in this case given by stowage factor is given to be 1.2 meter cube per ton, density is density is given to be 2 tons per meter cube, 1.2 minus 1 by 2 divided by SF, which is again 1.2 in. So, this is about 0.583, this is your permeability. Now, what you need to know here is, remember that equation I wrote, in that equation I said that the left side, I mean that equation which said that intact volume before bilging is equal to intact volume after bilging, it was like saying that the volume or it was like saying that the initial weight of the ship or the final weight of the ship minus the added weight is equal to the initial weight of the ship, okay. That is that equation. So, it is like this. Now, what I am trying to say is that when you take that in this, I will write this intact volume before bilging is equal to the volume after bilging. Or the volume before bilging is LB di, this is the underwater volume before bilging, equals LB dB, this gives you the volume after bilging. Now, you need to subtract the volume of water. Now, what did we used to do? We usually used to find the volume of the compartment. Okay. Now, what you are seeing is that it is not enough to find the volume of the compartment, you have to multiply it with the permeability, because only that much will be flooded with water. So, when you this is actually, this derivation came from getting the weight of water. So, to get the weight or the mass of water, to get the weight of water, that mu has to be multiplied, because only so much of the volume will be flooded. So, that is needed. So, in this case, if it is LBH, you have to multiply that mu. The whole volume of the compartment is not flooded with water, only the volume of the compartment into mu, that much of volume is only flooded with water. So, that is the only difference. If this is dB, if it is, that is, so this is so you are told that the length of the vessel is 100, 9 is the breadth, 5 is the draft initially. So, 100 into 9, and you do not know what is your dB, minus you are told that 20 meter length of 9 breadth is flooded into dB. This is, so the problem, there is nothing different except that in this equation which said that the volume of the water which is entering initially, for us the volume of the water that entered was L into B into dB, L B dB. Okay. Now, we just change that slightly, L B dB into mu, that is your only, that is the volume of water that has flooded. So, in this problem that is only difference, you multiply it with a mu here, this is the only difference. So, once you do that, you will get your dB, this is your dB. Then and in case you are asked to find Km, you do di by 2 plus b square by 12 d, b square by 12 d. Okay. And that is all, that will give you your Km, and that is one part of it. Okay. Now, we do a particular kind of problem, I mean we will derive a particular kind of that is, we are going to now do, you have a ship. Okay. Now, this what this section deals with is, so you have the ship of length here, and in this middle, suppose that there is a small region on, let us say that this is the center line. Let us suppose that at a distance, some distance from the center line, somewhere towards the edge of the ship, some region, small region there gets flooded in the midship part of the whole length, means in the midship means middle of the length, not the middle of the breadth, not this view. From this view, in this point, somewhere at the middle, at some distance, some point, some region gets flooded. Now, what will happen is that ship is like this. Okay. This is the whole length of the ship, this is the center line, and this region is flooded. Now, what we are going to do is, if this region gets flooded like this, it will sink. First of all, one more thing will happen, it will tilt, heel, not tilt, heel, it will heel like this. Now, we can find out by mathematics how much will be the angle of heel, what is the final list value, list angle. Okay. What is the final heel angle we can find. So, that is the section. Okay. Now, so you have so this is your so this is your initial water line W0 L0, and d, let us call this di, and now some region, this is the midship, this is what we are calling as midship. Okay. Now, at the midship, you know the sign, right? The sign says midship, that is the meaning of that sign. Now, now this gets, we will look at the plan view. So, this is the plan view, this is the breadth of the ship B. So, this is the breadth of the ship. So, this is equal to B by 2, this is also B by 2. Now, the problem is defined like this, some region, this is the center, just like now some region here, okay, a small compartment here gets flooded, this region, this thing gets flooded. So, this compartment region gets flooded, and so what happens is the ship will first of all sink, it will sink, and its water line is now here, W1 L1, and let us say that the water line has gone up to dB. This is your final draft, bilged draft. Now, what we are, that is the first thing that happens is that it sinks now, and the second part of the problem is that it starts heeling now, because it is only on one side. Okay, the compartment is not on the center line. If it is at the center line, there is no heeling, but it is now at a one corner, as a result of which the ship heels. So, we need to find the angle of heel. Okay, the first thing to find is to find the bilged draft, we need this figure. So, I will keep this here. Okay. So, first we need to find the bilged draft. So, the bilged draft is given by the formula weight balance we can do. This is the initial weight of the ship is equal to the final weight, which is L B D B minus L B D B. This will give you the bilged draft. This directly you can calculate. Now, so this is now the next one. Let us look at the ship from, so this one. Let us look at the ship from this point of view, from the front view, what we usually do when we find the meta center and all that. So, this is your water line, and this is after bilging. Okay. So, this is the water line, and okay, now this becomes a problem. See, that is this region is now your G. This is again we are doing, this problem is all very simple. Okay. We are all doing for box shaped vessels, such that your G, B, everything is very simple. You can directly calculate it from rectangle, square, all those kinds of volumes. So, the G of this vessel, since it is a perfect rectangle, it will be at the center here. Okay. G will be here, and but the problem is now this region gets bilged, G will not change. Remember, I have already said that G does not change in any of these problems. In bilging, we do not change G at all, but your B is changing. Okay. So, this will be your, this much volume is lost. Therefore, your B will initially when the vessel was upright and it was having no bilging, nothing, it was a upright vessel, G and B were in the middle. From when you look at it in this top view, G and B were exactly in the middle, because there is no volume here is equal to volume there, that concept you can assume that the volume is in the middle. But the moment this part gets bilged, some volume is lost here, B moves here. Okay, B is somewhere here. Somewhere here, B is shifted. Now, this we draw it here. So, let us assume that this is your G. So, this is your position of G, Now, as you saw in that figure, B was not at that point, B was somewhere slightly far away, slightly away. So, this is your B1, we will call it B1. This is the center of buoyancy after the ship is bilged, but before it has heeled. Okay. The ship has not heeled now, it has just bilged, sunk, and it is bilged, but it is not heeled, and that is that condition, and now it heels. Now, when it, so this is your G, and this distance, let us call this y. Okay, this position as y, this distance is y. Okay. It is the distance between G and B, which is your center of gravity and center of buoyancy. Now what happens? The ship, why is the ship trying to heel? First of all, the ship is trying to heel because G and B are now not in a same vertical line. When G and B are not in the same vertical line, there is a buoyancy, there is a moment acting, and the ship will heel to such an extent such that finally G and B will come in the same vertical line. Then the moment becomes 0 and the ship is more or less stable, okay, in that condition. That is why the ship is trying to heel. Therefore, now ship heels, okay, W0 L0, it heels to W1 L1 such that B1 moves to a point B2, center of buoyancy is now B2, and this somewhere here is your meta center MB. Everything same as in the previous sections where we are dealing with the meta center, okay, the sealing part. So, I will not go into that. Same thing, that is that vertical drawn from B which passes through G crosses the initial vertical at the meta center, that is what this is. So, this is head at the meta center. So, that is MB, and this is heeled through an angle, let us say phi. The ship is heeled through an angle phi. Now, so this is dB, that means it is the draft after the ship has bilged, then this distance, oh sorry, this is not y, it is in this book it is written as x. So, this distance is x, the distance between G and y is x, then this distance is h, okay. Now, what is h? H is the center of buoyancy of the bilged volume. Okay. H is the distance of the center of buoyancy from one edge, from this edge. Let us take this edge fixed, everything let us calculate from this edge distances. So, from this edge, this distance b you need to calculate, or the distance of the center of buoyancy from this edge needs to be calculated, that is given by h. Now, how do you find the centroid of center of buoyancy? Is always calculated as sigma moment of volume divided by the sigma volume. Now, so sigma moment of volume. Now, in this case, since it is a box shaped vessel, we can just calculate area, you do not need to calculate volume, everything is the same draft, everything is at dB. So, what you need to calculate is volume, this total volume, instead of taking the volume we take the area, because draft is the same in all cases, it is just constant. So, sigma moment of area divided by sigma area, that means this whole area moment minus this area moment of this area divided by the total area, that will give you the net center of, it will give you the net centroid of this area, that will give you the position of this B from this end. Okay. So, this H will be given by the moment of area.
Sir, to find B, we just take the area which is below the water line.
See, what has happened is, that is correct, but what we are, that is a good, what I am doing is, there is a box. Okay. Now, that what I need to find is the position of B, not the height, and I am not trying to find KB here, I am trying to find the position of B. So, I need to find this distance. Now, what is you have a whole box up to some draft, okay. So, some volume inside. Now, in this edge some volume is lost, that is a condition. Now, how do you find the position of B? You find the moment about the whole box minus the moment of this box that is lost volume divided by the net volume, that will give you the position of B, right.
So, but why total volume?
Volume underwater, not total volume.
Yeah, that.
Yeah, not total volume, volume underwater only, that is correct. So, that we never take total volume, whatever is the volume underwater into its B, position of B plus the minus the volume that is lost here, position of its B divided by the total volume, that will give you the position of B, right. That is what we are doing. Now, everything is this area divided by this height. So, and anyway we are trying to find the this coordinate of the center of buoyancy. So, what we have done is we are taking only that water plane areas moments instead of multiplying it with the height also. So, that will give you the position of the this position of the center of buoyancy, not this we are not needed. This anyway there is not, I do not think there is anything to do, because even if this volume is lost here, this height will still be kb with this dB by 2, because see you have a box, even if you remove one section from here, vertical position will still be at dB by 2, that is not going to change, it is only the horizontal position that will change, because some section is lost here. So, to find that horizontal section you need to take the horizontal moments, means moments from one, some horizontal moment means moment like this you have to take, not vertical moment. So, we will take it from one side right now. So, moment of area about one side divided by the net area, you can take area at the water line. So, this will give you, if you just look at this figure, it will become very clear what areas we have to take. For instance, it will be L into L is this length into B into dB, this gives you the L into B into, oh we are not dB, we are trying to find the moment of area. L into B is the area into what do we need? We need the centroid of its, remember we are finding the x coordinate or this coordinate, this distance, this is, if this is x, let us call this x, or y, in usually it is y. So, we are trying to find the y coordinate of the B, position of B. So, we multiply the whole area which is L into B into its B, into its center of buoyancy, what is it? It is B by 2, for the whole it is B by 2. When it is lost, when this section is lost from it, it goes here. Let us, I will call, I will not call this B, then I will call this B1. Okay. Initial B is here only, B0 is exactly at the center, because it is just a box, B will be exactly at the center for the area. B1, therefore, L into B by 2 minus this small volumes or this small area into its centroid. Small area is L into B, whatever is its this length into this breadth, that gives you its area. Now, into its centroid, it will be B by 2, small b by 2, okay, divided by the total area. This will give you h, this distance. Now, what we need to find, what we need here is another thing which in this, actually please spend some time, it is very simple when you read the book and when you see the derivation, it will become very simple. Actually, if you read itself, I mean when you are listening itself, probably it is becoming very clear. That is, see this distance h is this distance, okay, and it is the distance between this edge, in this figure it will be here, see it is the distance between this edge and B1, which is the center of buoyancy after Bilge condition, and this is your G. In this distance, okay, is G B1, or it is the horizontal distance between G. Note that B1 won't be, G and B won't be on the same vertical level, they might be different. So, anyway, but G and So, this horizontal distance between G and B is what we call as x. In this it will come like this, that position is, this distance is x, the distance between, what horizontal distance between B and G is x, it is this. Therefore, this x, as you can see from this figure, is actual to equal to h minus b by 2. This is h, this is b by 2. So, h minus b by 2 will give you this distance. Therefore, G y will be equal to x, which will be equal to h minus b by 2. Okay, this is your G y in this. This distance G y is now calculated using this formula. Now, what will be your K b? K b? Oh, it's not seeing. Okay. K b. So this is okay. Then K b is always equal to d b by 2. This does not change, whatever happens. The bilged draft divided by 2 gives you the K b of the final. Then okay, then we need to find the B m. This is K b. Then we need to find B m. B m is equal to I divided by del. Now, note that you need to find, usually you do not, you have to find, let me see, you always find I about, till now this problem has not arisen. So, we have not dealt with it. You usually find the I of the ship, okay, about the center line. We have done it about the center line. It is actually that center line, we did not define it very clearly. It is actually the centroid of the volume, the line through the, it is the volume, it is associated with the volume, means this volume is equal to that volume. That is how it is considered as a centroid. That is why it is called a center line, means the volume on left side or port side is equal to the volume on the starboard side, and that line was center line. Now, that means it is actually the line through the center of buoyancy, in fact. Okay, that y coordinate of the center of buoyancy is what is required. Now, this problem it becomes slightly more complicated, in that you see that the volume on one side is not equal to the volume on the other side. Therefore, when you define really center line, it is the centroid through B, means it is the line that will pass vertically through B. Okay. So, it is not the exact center, it is not the, because one side some volume is lost, it goes slightly towards the other side. So, that is the point through which you have to take I. So, in this case, this I always you are doing this, in this case, remember. So, in this problem it becomes I about which point? This line, this is the line, not about B by 2, this is B by 2, this was your center line in ordinary case, but in this problem it needs to be redefined, you have to do the volume about this line, I mean you have to take I about this line, the moment of inertia about this line h, I has to be calculated about this h. Now, this is the probably the only problem. You know that the way to calculate, there are different ways to do this. You can do one thing, you can calculate I about this point b by 2 and minus a y square, you know that formula, right? I about one point minus a y square, where y is the distance between the two. Or if you take, what they have done is, you can do I about this side, you can take the moment of inertia about this side minus a into h square, h is the distance, this distance. So, that will give you the moment of inertia about this point, it is moment of inertia about this minus a into this distance square. So, this is what needs to be done, this will give you your I about the point h, and then you get B m is equal to I by del. And then if you look at this figure, you will see that, remember in this problem our concern is to get phi, okay, tan phi. We have to find the list the angle of heel. So, tan phi, if you look at this problem, it will be equal to g y divided by y m b, and now g y we have already calculated using this. Right now here g y, as you have seen, g y is equal to, in this case, h minus b by 2. Okay, this was the formula for g y we just got. So, okay, therefore, tan phi is equal to g y by y m b. We will see how to calculate y m b in the next class. We will stop here. Okay. All right. Thank you.